Hello and welcome to another power electronics class. In the previous class, we went through the syllabus and we did a little bit of introduction on power electronics and the definitions of power electronics. Now, this week, we would continue with the introduction. We will go through different applications of power electronics and some examples of that. And if we have time, we would start with some design requirements of power electronic systems. So, as mentioned, we went through some introductions. What is the definition of a power electronics? Different type of converters, like such as AC to DC, DC to DC, and so on. And what is the definition of an inverter? What is the definition of a converter? Uh, what are some requirements? And a little bit about the market opportunities there, and some desired features that we mentioned. And as I mentioned, if we have a AC to DC converter, we usually call it a rectifier, and a DC to AC converter is called an inverter. Now, some areas of PE, we have the applications, the topology circuitry, the modeling and control, and power semiconductor components. I'll explain briefly about each of them. Some applications, I'm going to go through some of them. If you could think of some examples, please, let me know on each of them. The first one application is DC and AC regulated power supplies. Can you give me an example of this? The chargers that you have on your phones, the laptop chargers, all of them use a rectifier, which is a power electronic component. And we also have AC power supplies as well, which are sometimes used. One good example for that would be sprinkler systems. I don't know if you've looked closely into your sprinkler system, but the valves, the water valves, those are usually 24 volt AC. Okay, so that converter is a 120 to 224 volt, but you need to regulate that. You don't want the voltage to fluctuate. If it goes up, if you have a fluctuation in the input power voltage, it's going to translate to the output of the transformer, and it's going to damage your solenoid, the valves that you have, the sprinkler valves, and it's a tedious task to dig and take them out. So you need to have regulated voltage there as well. Another one is electrochemical processors and processes. Can you give me an example of this one? Yes. And also fuel cells is a good example. Now, fuel cells, if you put an anode and a cathode into water, you can separate the hydrogen and oxygen molecules. Usually they, let go of the oxygen, they store the hydrogen. Now, if you put that hydrogen back with a catalyst and you add oxygen to it, and you have a cathode and anode again, you can create electricity without burning, the hydrogen. There are two ways that we can do that. Generate energy, but fuel cell is a very, And another one is chemical reactions. Most of the times, if you think of a refinery, you may think we are melting something and adding chemicals and extracting something. It's most of the times that's true. Sometimes when you're, for example, extracting copper, the way that they extract copper is they actually put an anode into the melted, into the melted metal, and then they put a certain voltage, like 2.3 volt or something, and selectively extract the copper. So it's a DC selected voltage, and it just the copper, molecules bond to it, and then you have these copper sheets. I don't know if you have ever seen a copper, processing. Have you seen any? And you can see, I'll show you how it's done. So again, as I mentioned, you can see that at the end, when they want to extract it, they will put these huge metal sheets It's called the electrolyte refining of the copper, and they just put it into these liquid, and they would put certain type of voltage, and they would extract copper. Now, maintaining that voltage, if the voltage fluctuates, then you're gonna extract different type of metals, and you don't want to do that. This copper is like 99% pure copper, so you need a very selective way to do that. And the only way to do that right now is through a DC, very controlled, precisely controlled DC system. And to do that, you need power electronics to be able to convert AC to DC and have a controlled DC voltage. Another one is heating and lighting control. Now, some heating systems are using power electronics, not all of them. And also lighting controls, if you want to dim the light, now these dimmers, a lot of them are using buck converters or boost converters, so you can precisely control the output of the light. Now, light intensity is mentioned in lumen. Usually lumen is the amount of light that is that one candle, or they call it candela as well, emits. So you can precisely now control if a light has 200 lumen outputs or 3000 or so on by controlling the voltage precisely using a power electronic tubes. Another application for power electronics is these electronic weldings. I don't know if any of you have experience with welding. 15, 20 years ago, when I used to do welding a lot. I was doing a little bit in mechanical engineering as well. I did a minor in that, and then we learned how to do welding with those old machines. The old AC weldings. They were huge because it required a huge transformer. It reduces the voltage to around 50, 60 volts, and increases the current to 200, 300 amps, depending on what you want to. But the problem with those welding machines were very big and bulky. And then came these solid state, electronic welding machines, which are now pretty small. It's as small of a suitcase. Have any of you seen these newer generations? So the way that they're able to do that is through switching. So instead of having these large transformers, you can do that basically by having a high power semiconductor switch and a small transformer. So we got rid of a lot of that. The good thing about this is that you can precisely control the current and the voltage. So, weld sticking, or if you have like a cheesy, spot, or, cold spot or something like that, that's now completely eliminated because you have a precise control over the temperature and the current and the voltage. And they are much faster as well, much easier to move and so on. Now, if you want, I can compare to different type of them.
And welding, it seems to prioritize higher amperage over higher voltage because the heat loss is relative to the square of the current. So it is creating a higher heat and
yes, that's correct partially. But the thing is, high voltage on its own, if you have 10,000 volts and a few amps, milliamps, it's not going to heat up as well. It's going to quick. So the thing is, it's going to give you electric shock. First of all, it's not, yes, obviously, the relation is I square R. So the higher the current is, you're going to create more heat. And on top of that, you want it to be safe. No one wants to work with a welding machine that is 10,000. That's like a lightning. Technically, it could in theory work, but it doesn't make any sense. Before you even start, so the thing is, when you have very high voltage, before you even start welding, you're going to have the electric arc. When you have 5,000 volts, you're not going to even start, welding. Before that, you're going to have electric shock. But there are certain reasons. And the thing is, the voltage is usually, you keep that at a certain point, like 50, 60 volts, and we change the current depending on how thick the metal is. So for some applications, like 60, 50 amps, for some is 200, 300. So if you're doing a pipe or a square pipe or metal sheet, depending on thickness, the type of steel that you're using is going to be completely different. Now we have argon, gas that we add or so on. There are different, like maybe 50, 60 different type of welding machines. But you can see that nowadays these solid state ones are very, very small compared to the older ones. And these are the older ones that when I was, a student, we had these big red ones, which had wheels. And now they are replaced with these tiny machines. And they are doing the job that they're doing it's much, much easier than the previous generation that we had. And I'll explain about the inner circuit as well a little bit when we get to that one. Now, another application is power line volt-amp reactive and harmonic compensation. We learned that for power factor compensation and to reduce the reactive power, increase the real power, what we did, do you remember what we did? Was that we added a capacitive bank for power factor correction. If you remember that, I don't know if you had measurement instrumentation with me and power system analysis, but what we do is usually we use a capacitive bank. Sometimes we don't have enough space and we can't implement that. So we do that using power electronics. I'll explain how we can do that and do power factor correction as well. So one simple way that we can do that is that imagine you have an AC signal coming in. Power factor is pretty low. We want the power factor to be close to 1. Imagine it's 0.6, 0.7, which is awful. One way to fix that, if we don't have any capacitors, anything to compensate, and the problem is the power factor is fluctuating as well in the system, some systems. So what we can do is we can convert that to DC and use a very pure good inverter to convert back to AC. And then we got to get completely rid of that reactive power. So that's one way to do it. And we have precise control of the power factor in that case. Then we have high voltage DC systems, which we call them HVDC, photovoltaic and fuel cell conversion. Obviously, we have inverters to convert DC to AC. We have variable speed, constant frequency systems, and we have solid state circuit breakers. So variable speed, constant frequency systems is what we mainly use to control AC motors. As you know, synchronous motors, the speed of the motor is relevant to what? To frequency, to the input frequency, okay? If you remember, it's 120 F over P gives us the ramp per minute or N. So the higher the frequency, the P, which is the number of poles of the motors, you can't change it while the motor is changing. Obviously, it's the characteristic of the motor. The only thing that we can change is the frequency to change the RPM. Now, if you have an outlet, 120 volt outlet, the frequency is fixed at 60 hertz. So that's the reason single phase AC motors that we don't have any control over its speed, okay? But if we have an AC to DC converter and then a DC to AC inverter, and in that inverter we can control the frequency, we can precisely control the speed of the motor. So instead of the motor turning on instantly and going to its maximum RPM at the start, we can slowly increase the RPM of the motor. This is exactly what happens in these inverter, HVAC, and fridge and freezers. So from 10 years ago, you can see everything has an inverter, like an inverter, HVAC or inverter. So the good thing about these motors is, so previously what happened in a refrigerator, the ones that don't have an inverter or an HVAC, is the compressor would turn on for like 20 minutes and then shut off, and then turn on and then shut off. And that creates a lot of waste in the system and heat, and it degrades the components of the system, the compressor. But the newer inverter system, and the motor can go only from 0 to 100%. You don't have anything in between. But for inverter, DC they call it, or AC, now they can precisely control the speed. So they could go from 0 to 10% to 20% to 50% to 100% down back. Now that's useful when someone just opens the refrigerator door and closes it, because you don't need to, turn on the system for 10 minutes, drop the temperature like a few degrees below it, and then shut it off. You can just turn it on for 20%, at 20% max, cool it down at the temperature, and then just shut it off. And it has, I think it's around 70, 80% sometimes power efficiency over normal system. And the components will last longer. But the problem is that AC system is pretty simple. It just has an on-off switch. This one requires an inverter, which makes it more expensive. 10, 15 years ago, it was like double the price if we bought an HVAC system with inverter. Now it's like 10, 15%. I don't even see the older generations, because the amount of energy saving that is in like 5, 6 months would compensate for the extra, investment that you do up front. A newer generation of that is now heat pumps. I don't know if you heard about that. So now they are inverter heat pumps. Inverter heat pumps, they can even generate, so they cool and they heat. And when it's heating in the winter, it's like reversing the compressor. So the compression side is done inside and the evaporation side is done outside. And even when you're at like 30, 20 degrees outside, so you have enough energy to take from that and deliver it inside. And those heat pumps, they have significantly increased the efficiency again. But again, because you have 2 evaporations and 2 compression cycles, it's going to increase the price about 50, 60%, but it will return the investment in a few months. So these are the latest technologies that we have in HVAC and also on refrigerators. Now, a different type of example for these variable speed, constant frequency systems is, again, if you have a constant frequency, you want to now change the voltage or you want to change the current, okay? Then power electronics comes into place as well. And it's also used in motor drives as well, for stepper motors, for BLDC motors in drones and so on. You can precisely control the speed of the rotation. The reason that we didn't have, 20 years ago, we didn't have a drone was that we couldn't precisely control the RPM of each propeller. That's the reason the drone would simply flip. But now we can, control it up to, so it's like 5,000, 10,000 RPMs. Now we can, control it up to 1 or 2 RPM. So it's like 0.001%. We can control it and prevent it from flipping. There's a famous picture that I always like to show. Now, this is a very famous picture, interesting picture. We went from the upper one to the lower one in the span of 10 years. And the drone is much more high quality than we ever had. In 2009, 2010, if you want to take an aerial video, you need a helicopter, you need a pilot. It's dangerous. If you want to shoot a movie, imagine that you want to take a selfie on Instagram and you hire someone with a chopper and a cameraman. Imagine the chaos it creates. And you want to take it in a public space, okay? A national park or something like that. And then now it's replaced with a drone. And the quality is much higher than that. And now we have these FPV drones that goes into these, small spaces that a helicopter would never do. So this is actually all done by, I would say most of it is just power electronics. Because we had most of these components in the last 30, 40 years. But we were able to make the battery lithium ion, we had it from 91. Sony actually came up with it. The digital camera is from Kodak actually. And they invented that in the 80s actually, late 80s. But putting all of them together, making a small footprint, and the BLDC motors, power electronics, the electronics behind it was able to, transform the technology. Now, another one is induction heating. Again, we can use elements or we can use solid states in power electronics, which I would explain later and I'll show you some examples. Now, some other applications, you can see that now we're using smart grids and microgrids, we can communicate between these power systems, these smart grids, there's renewable systems, and we can synchronize them. If there is a surge in demand, we can increase the production or the power plant, and it goes from the production down to consumption. Everything in between is now has a power electronic component. We can maximize the efficiency in the consumption, and we can also do that in production if we have a solar panel. Solar panel is technically a power electronic too because it's a diode solar panel. So now, some applications of it, for example, home appliances, we have it in the refrigerators, as mentioned, for inverter motors, washing machines, automatic door openers, cordless drives, vacuum cleaners, food warming trays, audios, and RF amplifiers. Now, one example that I don't know if you've seen these solid state coolers. And this is a very interesting thing. So these are called thermoelectrics. I don't know if you heard about thermoelectrics. When I was a student, they just came out. Thermoelectric is they're basically a type of, I would say, the solid state device. And when you connect it to a voltage source, it's very interesting what happens. Yes, one side gets hot, the other side gets cold. Okay. And it's very good if you want to use it as a heat sink in a place that you can't put a fan. And actually, some of these car refrigerators that don't go very, don't cool down very much, they are using this. Okay, if you use multiple of them and use a fan on the hot side, it's going to actually go down to freezing temperatures as well. So it's a system with no moving parts. Like it would heat on one side and cool on the other side. Now, some of them, if you change the direction of the current, it's going to do the opposite. It's going to heat on the side that cooled previously and make it cold on the side that was heating previously. Now, if you connect it as a refrigerator, and so one side is the cold part and the other side is the hot part, the amount of cooling that it does is the difference between the temperatures between the hot and the cold. So if you put a fan on the hot side, it's going to actually reduce the temperature on the cold side as well. So what it does, it's going to reduce. So it has a temperature difference of like 10 degrees. If the hot side is 80, the cold side would be like 50 or 60, something like that. Now, if you reduce the temperature of the hot side to 60, the cold side would go down to 30 or something like that. And they last for a very long time. And also the good thing about them, they're extremely cheap. This one is, I bought them for $1 or something like that. And you can see that they are actually building coolers from them. Most of these car coolers that you can see in the center of the car, which don't have compressors because compressors are cumbersome, they're big, they're expensive. They mainly use these small coolers that they are using these, or what we call thermoelectric. And you can see this is the principle behind it. So adding a heat sink would actually increase its efficiency. Now this is technically a power electronic tool, and we can use it again, as mentioned, for cooling. And for these hot trays, you can use the hot side to heat up a tray or something, and it gets very, very hot actually. The efficiency on heating up is much more than the cooling down part. Now, another application is electric power systems, like electric power quality, power factor correction, VAR, volt ampere active compensators, flexible AC transmission systems, or what we call FACTS, high voltage DC, and harmonic reduction. All of that is done usually through a converter, inverter, something like that, or AC to AC converters. Automotive industry, we have the electric and hybrid electric vehicles, power steering, anti-lock braking, steer-by-wire, brake-by-wire, starter, alternator, air conditioning, electronic ignition systems. And they have become very popular since the rise of, hybrid vehicles, when the Prius came out. The problem with those hybrid vehicles, most of the time when you're in traffic, the motor turns off. So when the engine turns off, the main combustion engine turns off, they had a problem. The problem was in the design, was that when you lose the engine, they didn't have any belts. So you're going to use power steering, you're going to use the brake booster, because these brakes are usually, they have like gas boosters, which is connected to the exhaust and helps you boost. I don't know if you worked on cars, the brake boosters. So it helps you to brake. And power steering, again, it's a small motor, small hydraulic pump that is connected to the engine with a belt. But the problem is when the engine is turned off, it's not going to move, so you're not going to have power steering. You're going to lose power steering. You're going to lose boosted brake. Technically, you're going to use like 80% of your brakes power. And you're going to lose your HVAC system as well, because, again, the compressor for HVAC for the car, for the AC, is directly connected to a belt to the engine. So what they had to do is they had to make all of them electric. So that's the reason they went for power or electric power steering, electric brake systems, electric HVAC systems as well. Now, the good thing when you go electric is the wear and tear becomes significantly less. Now you don't have a belt, a pulley, you don't need to maintain the belt. The motor doesn't run 100% of the time. In idle, when the heat, sometimes in the morning you don't have a lot of, the motor is cold, it creates like 30-40% of wear and tear on the entire cycle of the engine life. So that helped on reducing stress on the motor, on the engine. And on top of that, you can precisely control how much power steering you need, for example. So for cars that are electrically assisted power steering, which has become widely available, and now almost all internal combustion engine cars even have, is that you can control the power steering via the ECU or the car computer brain. And one advantage of that is that you usually need a lot of power steering assist at low speed when you're in a parking lot. But at high speed, that's actually dangerous because it makes the steering very light and dangerous. So now the computer, these new cars, they will send signal to the power steering and reduce the power and make the steering stiff at high speed. So it's safer at high speed. Now you have a precise control or how much power assist you need at different speeds. This is one example. The other example was HVAC. Previous ones, because it was connected to the motor, the engine. When the engine engine rev went higher, the compressor was going faster, but you didn't need that, much, compressor. So then they had to add a clutch to the compressor. So these older cars, most of the HVAC has a clutch actually, because the compressor is connected to the pulley, to the engine with a pulley and with a belt. It's running 24 all the time. When the engine is on, the compressor is the pulley of the engine. But we don't need the compressor obviously in winter. So they had to add a clutch, and it made it heavier. And clutch, obviously, we have wear and tear after 50, 60, 100,000. The clutch went out, and when the clutch went out, you had to change the whole compressor because it's difficult to, it's not worth repairing the clutch and the compressor. Now you had to change the compressor. You had to change the gas in the HVAC and the oil and the gas, and so it was but now with the electric ones, you can precisely control how much HVAC you want. You can cut the power. You can give 30%, 20%, 50%. And they don't use the piston wise. They use the heli. I don't know if you've seen one. It's like a snake type compressor. It's good to know. It's, general information that you can get. So now, they are using a type of compressor that looks, yeah, this is the way that they are compressing the gas. It's called the orbiting scroll. So instead of having the piston, so the older generations that had the piston, this one has a, orbiting scroll and a tip seal that continuously moves, and you don't have that knocking when you had in a traditional HVAC system. Traditional HVAC, car HVAC systems, they had multi-compressors. It was like an internal combustion engine. Let me show you how they worked. It looks like this. Can you see there are multiple pistons that push and compress it? The newer generations that use the spiral one, which is a higher efficiency one. The latest generation actually use heat pumps as well. Like the new Tesla and the new EVs, they use heat pumps because they don't have an IC engine for heating up the car. So in winter, the warm water that goes around engine goes to a radiator and air blows into the cabin. That's the reason that early in the morning when the engine is cold, you get very cold. But in an electric car, you don't have an engine. So the way that they do it, they are doing it 3 different ways. Some companies are using an electric heater, like an element that you have, induction heater or something like that. Problem with that is it's extremely power consuming, so it's going to reduce the range significantly. Some companies use the wasted heat generated from the battery because these batteries are water cooled. They send it to a radiator and blow the air through it. The problem with that, again, during a cold winter, when you start the car, it takes a lot of time. And the newer generations, they use a heat pump. So they use the HVAC for cooling and also for heating up the car. So that's different ways that, again, all 3 require power electronics to do that. Now, also ignition system and alternators, with the rise of hybrid, not just electric cars. Again, when the engine stops, you need a way to keep the 12-volt battery charged. Hybrid cars, all of them have 12-volt batteries on top of the high voltage batteries. And those 12-volt, even EVs, some of you may not know this, but all electric vehicles also have a 12-volt battery. That 12-volt battery is essential to, do simple, electronics running, like keeping the door locks with a remote control, or even opening the latch for the EV charger. If that EV battery, the 12-volt dies, the whole car stops working. But the problem with the EV cars and hybrid, they don't have an engine to run an alternator with a belt to keep the battery charged. So what they do, they use the high voltage battery and they use a buck converter to reduce. It's a DC to DC converter, and they charge the 12-volt battery using the high voltage, like 800 or 400 or 250 volt main battery that they have. And it's the same for hybrid cars. Did any of you had hybrid cars in the past? No. Have you seen where the 12-volt battery is in a hybrid car? Yes, some of them are beneath the floor. Some of them are actually in the rear. So almost all Toyotas that I've seen are in the trunk, the 12-volt battery. And the reason they put it there is actually sometimes it's closer to the hybrid, the nickel battery, the hybrid battery that they have. So, you don't need it to be close to the engine. to the alternator. You can put it anywhere in the car. So they usually put it in the rear of the car, which is more space. They have that flexibility. And also for EV, some of them it's in the front, some of them is also in the rear. And when it's the rear, actually it's safer as well, because if you have a crash, you don't have that acid, floating around. Yes, please.
Why is it better to have a separate 12-volt battery and recharge that from the main car battery instead of just having everything tied into the main car battery?
That's a great question. So the thing is, in a normal car, some things just run on 12-volt battery, okay? And we need that to be isolated. The reason is when you are charging, for example, the battery, or you're accelerating, the battery is under a lot of stress and you have a lot of fluctuation in the voltage, and you don't want that to translate to like an ECU or something like that. And on top of that, that 12 battery is easily swappable. So if something goes wrong, you can easily take that out. But you can't, swap out the whole battery of a car. It's going to be very, very difficult, Sometimes you want to disconnect the main battery when you're towing, for example, but you need to still have braking and lights and so on. That's the reason you want to separate and have a backup. So there are multiple reasons, just one reason. I would say like 10 different reasons. This was actually my question. Well, why don't you just use the main battery and have a buck converter? The thing is, you want to have redundancy. Sometimes the brake runs on that 12-volt battery. When you tow it, you need that 12-volt battery, but sometimes you can't even use when it's in an accident. There is an automatic system in an EV that completely cuts off the main battery. Even if it's a small minor fender bender, I've seen that a lot. The battery, the system, the computer automatically disconnects the main battery completely. But it needs a backup to run the system, to just keep it on, to, if you want to open the door, take someone out. So if there's an accident, the main battery shuts off. But the problem with most of these new cars is that they have these retractable door handles. Have you seen those? They automatically come out. Those run on the 12 volts. Because if the main battery, in a car crash, that dies, and then you have to take the people out. Actually, in China, they recently completely banned that because there was a few accidents that people couldn't get out. And there was an accident like a few months ago, unfortunately, that a few teenagers got stuck in a Cybertruck and they couldn't get out because it doesn't have a door handle. It's stainless steel, you can't get in. The glasses are very thick, you can't break it. And unfortunately, a few teenagers, it was a fire and an unfortunate situation. Now they're actually suing Tesla to, have an alternative way to get into it. Especially when you're inside, there's not a door handle. You have to take out a part of the, door panel to reach a small wire to pull and open it. And imagine if someone is in a situation that the car is on fire, the glasses are bulletproof. It's like technically an oven. So that's some problems with having too much electronics. You need to have mechanical backups. So the 12 volts is a backup system. Yeah. But great question. Now, another one is aerospace, aircraft and spacecraft power system, international space stations. A few decades ago, everything was hydraulically connected. Now we have fly-by-wire systems that everything, so everything is connected to wire from the cockpit, and we have like multiple wires for redundancy, and then it's connected to an actuator or a pump at the end and controls the flaps and so on. So you don't need to run a hydraulic, pipe from the tip of a 737 to the end to, send a command to a flap or something like that. And it's much faster, much more precise. Previously, the reason that they didn't do it is for safety reasons, but now they have redundancy. So they have a backup for a backup. Usually have like 2 or 3 backup on an airplane. So if one fails, the other one goes, goes on and works. Now, another one is telecommunication, like wireless communication power supplies, uninterrupted power supply systems like UPS. UPSs are technically big power banks that are connected to these communication towers and computers and usually hospital equipments. And they are always charged up and the power runs through UPS. So if the power from the grid is cut, the UPS automatically kicks in. It has batteries and it supplies it with power. The difference between a UPS and a backup system that you may have at home is these are uninterrupted, meaning they kick in microseconds without even the consumer realizing that the power was cut off. They are very, very fast, and they are built to protect like devices like such an MRI device, which are very expensive. And if you lose power for a second, it may, the coolant would drop and warm up, and you're gonna destroy the device, for example. Telecommunication systems, the newer generation cell phones, we use 5G and hopefully in future 6G. They are using higher and higher frequency. The problem with high frequency is that the higher the frequency goes, the range decreases, okay? So 4G has a much higher range than 5G. 3G has much better than 4G. 5G is actually so sensitive to different objects that even if it's raining too hard, it's showering, you're not gonna have good reception because even heavy rain would interfere with the signal. That's the reason 5G actually doesn't pass through walls. If you want to have 5G in the room, you need to have a 5G modem in the room, okay? Most 5Gs that you see on the phone, it's not 5G, it's technically 4G plus. It shows 5G, but it's not. 5G technically just can't even pass a very thin, wall. Now, the problem, again, when you can't pass walls and can't enter the building, you need to have multiple transmitters. So instead of having one in 1 square mile, you would have 10 or 20 in 1 square mile. And on top of that, you have mountains and buildings. So if there's a building on the way, you have to have another one behind the building. Or if there's a mountain, actually, the mountain, what it does is sometimes it reflects the signal. So now you have to correct for that. I don't want to get into the details. But for the fourth and third generation, there was like one, what we call BTS or tower for 20 square miles. And it's a very high frequency signal and high power. The only way that you can do that is with a power electronic. 60, 70, 80 years ago, they used these vacuum lamps as the transistors for high power transmission of AM, FM radio. Now that's replaced with power electronics. And they are doing all of it with these power transistors and so on. So for telecommunication, when you want to have high frequency, high power, because you have to send a high power beam, microwave beam for long distance, the only way to go is using power electronic systems. Next one is transportation, locomotive. We have electric and hybrid electric buses, magnetic levitation as well. One thing that I usually like to show the students is mining trucks. You've already seen these, and have you seen how enormous they are? They are massive. This is a comparison. This is a good comparison of how massive it is compared to someone sitting close to it, okay? And this is a small one. This is not like a 300-ton one. You can see its size with the comparison with Silverado. Now, you may think that these are run by diesel. They have a diesel engine in them, but the diesel engine is not connected to the wheels at all. In the front, there is a huge diesel generator, like a 500 kVA or sometimes 1 megawatt. And that is just for generating electricity. And in the real axle, there are 2 large electric motors, usually 1 or 2, 1 megawatt each or 500 kilowatt each. And they actually run the real wheels. So this completely separated. Front is for generating electricity, and it runs electric motors. The reason that they do that, if they wanted to directly connect the engine to the internal combustion engine to the wheels, you need a huge transmission case and clutch and so on. And on top of that, still this system, this is a small moving truck, but it has enormous amount of torque. The advantage of electric car motors is you have maximum torque at this big start. For internal combustion, you get that around like 2,000-3,000 RPM or 1,500 RPM for a diesel engine. For an electric, you can get it instantaneously from start. It doesn't require any maintenance, so sometimes you just leave it for 20, 30 years. An electric motor. It's cheaper, easier, very quiet, and you have precise control on each wheel. That's the reason they usually have two motors to control each wheel to gain traction when you go up a hill in a mining field. So now you have a generator that generates electricity, but you need to control an electric motor, AC motor. How do you do that? If you have an AC motor, which you control the frequency, you have to do it using power electronics, okay? And another thing as well, these are also electrically powered. They are diesel electric. You may think they are running on diesel, not at all actually. They have a diesel generator in the front and the wheels are actually turned with electric motor. Did you know that? So almost all, I would say close to 100% of locomotives are run by electric motors. These are called diesel electric. They are like $2-3 million each. And the way that they actually work, I can show you how it works. This is the engine, and there are two electric motors on the wheels. And it's also the same thing for subways and maglevs. So all these heavy equipments, you may think they are running on. The diesel is providing the power, but the main propellant system is actually yeah, this is the electric motor, and it's inside the axle. You can see it's a pretty small motor. I wish I could show you another one. Yeah, this is the ones that are on the axles of the motor. So transportation again, and there's no limit to the power. You can see high-speed bullet trains, they go for 200-300 miles per hour easily without making any noise or sound. The problem again is the battery. If you had good batteries, they could run on electric. That's the reason if you have like these cable hanging locomotives that they have the cables on the top, you can run them indifferently, or the subway systems. They usually power them through the floor. So the rail itself carries electricity. They have like an extra rail that powers that. Most subways. Some of them are from the top. Some of them are actually getting power from the rail itself. And then we have commercial, which are electronic ballots, light dimmers, hand power tools. If you have any of these DeWalt or a Milwaukee or something like that, yeah, most certainly you'll see that the newer generations, all of them, it says it's brushless DC motors, because those brushed ones, you need to change the commutator and it's going to be it requires maintenance. But the new generation, all of them are BLDC, that they don't require any maintenance. It's very powerful. So you have a small tool, which is extremely power, running on 20-volt battery. And I've even seen jackhammers with them, which could break concrete easily using a small, tiny brushless DC motor. If you open it, it's a brushless DC motor size of your fist, maximum. Very small, very, very powerful. And then we have industrial, medical, which are fitness machines, laser power supplies, medical instrumentation. And then we have industrial, which are movers, machine tools, induction heating, elevators, timers, pumps, compressors, printing press machines, dryers, contactors and circuit breakers. Some other applications are robotics, computerized control systems, active filters, converters, integrated circuits, fuel cells, adjustable speed drives, industrial automation systems, and so on. Now, here is a very nice example of a traditional system on the left and a system optimized using power electronics. So imagine that if you wanted to pump water, previously, if you wanted to do that like 10, 15 years ago, even now, if you want to run a cheap system, you have an AC motor. The AC motor runs at a specific RPM. You can't, control the RPM. It's connected to a pump. And the only way that we could control the output flow of the water is using the throttle valve. So there was a valve, you can control it manually or electronically. And so imagine if you have a power wash machine, the only way that you can control it is having a physical valve at the end and, opening and closing that. Now, what's the problem with that? The problem was that most of the time, you're going to put pressure on the motor because you're limiting the output. So you're reducing the components lifespan. The pump itself, it's going to be under stress. The motor is going to be under stress. And on top of that, you're wasting a lot of energy. You're putting 2 kilowatts into it, for example. The amount of pressure you're getting is equivalent to a 1 kilowatt motor, for example. Now, the newer way to do it is just use the adjustable speed drive, which is a BLDC motor that you can control electronically. And instead of having 100% RPM, you could put it at 50%, 40%. And then you don't need the throttle valve, and you can just control it simply by changing a knob or even doing it automatically. It's like having your light dimmer, but on a motor, so you can control the output. Now, this one lasts 2-3 times more, and you're going to have better energy efficiency. It doesn't run hot. The motor, the previous one, it's going to be under pressure and it's going to get pretty hot. And the same thing for power tools as well. So power tools like 10, 15, 20 years ago, the ones that plugged in, you could, like a drill, you can just go at a single speed. But now the newer ones, you can gently push it and go from lower speeds to high speeds. That's the reason we have these electric screwdrivers. Like 20 years ago, we didn't have them because you couldn't control the speed. And the good thing is, even at very low speeds, you have maximum torque because it's a DC motor, brushless DC motor. So you don't need to put it on maximum speed to have a maximum torque. And that's some benefits of the system. So conventional drive wastes energy across the throttle valve to adjust flow rate. And using power electronics, motor pump speed is adjusted efficiently to deliver the required flow rate. Now, another example is switch mode power supply. If you look at the transformers that we had for charging the laptops 10, 15 years ago, they are bulky and heavy. The reason is that we needed a huge transformer to step down 120 volt to 5 volt or 10 volt, for example. Then we use a rectifier. Now we don't do that. We use power electronics to minimize it. That's the reason we have the GaN. If you look at these new power supplies, they are extremely small, but they're very powerful. Now, the way that they do that, and I opened, if you open a hairdryer, you can see it in that as well, is that in these new systems, for example, one system that they use is instead of using a transformer in the beginning, and this is a good example that it shows. So the previous systems, they didn't have this part. You had a transformer, it went from 120 volt directly to 12 volts. And this transformer needed to be huge, okay, if you had high power. But now, instead of that, what we can do, we add this small diode, and what this diode does is instead of having this voltage in the input, you have a half wave in the input. So you have this in the input. This cuts the signal in half. Now, instead of having 100% power coming in, you have half of the cycle coming in. So you can half the transformer because you're halving the energy coming in then. So you need to you can halve the transformer. And on the other side, we have two other diodes to rectify it and so on. So adding the small diodes and a switching system, instead of having the whole system, power coming in, you can have cut it in half at the beginning, and you can halve the size of your transformer. And it's the same thing in a hair dryer. If you look on your hair dryer, it has different levels of heat or speed. You have high and low, okay? When you put it on high, the input is connected directly to the outlet. It's 120 volt. When you put it on low, it runs through a diode, and that diode cuts the signal in half. Now the heat that is generated is half. So by simply adding one diode, you can halve the power that goes into your hair dryer, half the heat, and half the fan speed as well. Okay, so very, very simple system. If you wanted to do it through a transformer, you imagine a huge transformer was required to drop the power in half, and you needed a resistor to. It was going to be very complicated. But with a single power electronic tool, you can make that happen. Okay, that is it for today. We are out of time. And if you have any questions, just please let me know, and I will see you next week. Thank you so much.